Welcome to ScienceCover.com. Today we're going to look at conservation of energy. We're going to look at what the law of conservation of energy is. We're going to look at using conservation of energy with objects that change their height. And we're going to look at how we draw Sankey diagrams. If you think about where the light energy comes from, that is produced by a light bulb, we are putting in electrical energy. Electricity is entering the light bulb, and this is creating light energy. However, if you look at the amount of light energy that's being created and you compare it to the amount of electrical energy put in, they're not equal. There is more electrical energy going in than light energy coming out. So are we losing energy as the energy is traveling through the light bulb? Well, no, because we're also producing heat energy. And that heat energy is wasted to the surroundings. However, if we look at how much light and heat is produced, we find actually that's the same amount of energy coming out as what we put in as electrical energy. Now this is the conservation of energy. This is the idea that the energy is not created or destroyed by that light bulb. So we can summarize the conservation of energy as energy cannot be created or destroyed. It's only changed from one form into another. Pause the video and complete task 1. Let's have a look at the answer to task 1. The law of conservation of energy is that energy cannot be created or destroyed, only changed from one form into another. So the missing words are created, destroyed, form, another. What happens to the wasted energy lost by any device? The energy is lost to the surroundings as heat energy. So the missing words there would be lost, surrounding, and heat. Around 1590, the Italian scientist Galileo dropped a heavy and a light cannonball from the top of the Leaning Tower of Pisa to investigate their speeds. What do you think happened? Well, the result was that both hit the ground at the same time, and he showed that falling objects all drop at the same speed. Now, if you imagine he carried his cannonball to the top of the tower, that'll have gained height, and so it'll have gained gravitational energy. Let's say that he gained 5,000 joules of gravitational potential energy. But since the ball is not moving at that time, it has no kinetic energy. But when he dropped the cannonball, it will start to move. But at the same time, it also loses height. So the gravitational energy becomes lost, but the kinetic energy is now gained. When the ball reaches the ground, it will have no height energy. So its gravitational energy is going to be 0 joules. So where's all that gravitational energy gone? We started with 5,000 joules. When it hits the ground, it's got 0 joules. And the conservation of energy says that we can't destroy that energy, so it's got to go somewhere. Well, the answer is that that energy actually becomes the kinetic energy. So we should, without having to do any maths, be able to calculate that if we started with 5,000 joules of gravitational energy, and that's gone to 0 joules of gravitational energy at the ground, then our kinetic energy must have done the opposite. It was 0 at the start. It must now be 5,000 joules. We can look at the same idea of a child going down a slide. At the top of the slide, we've got height, and so let's say that we've got 1,000 joules of gravitational potential energy. Now at that point the child's not moving, so the kinetic energy will be 0 joules. But as soon as the child starts to move down that slide, they're going to lose height. And when they lose height, their gravitational potential energy will get lower. Since it can't be destroyed, it's going to have to turn into a different form, and so it turns into kinetic energy. So by the time the child gets to the bottom of the slide, all of our gravitational energy should have been changed into kinetic energy. So we started off with 1000 joules of gravitational, we'd expect to end with 1000 joules of kinetic. Pause the video at this point and attempt task 2. Let's have a look at the answer to task 2. Between A and B, we are losing height, so gravitational potential energy must be lost, but therefore we will gain kinetic energy. So GPE turns into kinetic energy between A and B. As we move from B to C, kinetic energy is being lost, but gravitational potential energy is being gained. So kinetic energy is turning into gravitational potential energy. Why does the pendulum lose height over time? It loses energy to friction and air resistance. What happens to the energy lost to the system? It'll all be lost to the surroundings as heat. The Sankey diagram is a way of showing how energy changes take place in a system. The left-hand side shows the energy going in, and the right-hand side shows what the energy becomes. The width of the arrows represent the amount of energy. So let's imagine drawing a Sankey diagram for a light bulb. We've got electrical energy entering the light bulb, and then we know that both light and heat are being created. So we need to show one arrow for light and another arrow for heat. Let's have a look at a second example for a gas hob on a stove. The gas contains chemical energy, a stored form of energy. And that energy will be burnt to produce heat energy. We'll also see some light energy. And it may even make some sound energy. Pause the video and try task 3 and task 4. Let's have a look at the answers for task 3. The Sankey diagram shows the energy changes taking place in a television set. So we've got electrical energy going in on the left hand side, and we know that the screen is going to be producing light energy. We know that sound energy will be given off and wasted energy in the form of heat. How does the Sankey diagram show that energy is conserved? The width of the arrows carrying energy in, the width of that electrical energy, is the same as the width of the arrows coming out. So if we add up the light, the sound and the heat energy arrows width, they should be the same as what we started with. How much energy is lost as light? Well, if we're putting in 50 and 10 joules has become heat and 10 joules has become sound, it leaves only 30 joules to become light. Task 4. Sketch a simple Sankey diagram to show the energy changes that take place in a laptop computer. Well, we've got electrical or maybe chemical if you're thinking that it's battery powered going in on the left hand side, and the screen will produce light, the speakers will produce sound, and again we'll have a wasted form of energy as heat. Sometimes you're asked to draw a Sankey diagram to scale. Now to do this you have to look at how much energy is going in. So we've got 20 going in, and we know that 15 is turning into heat, and we're wasting 5 as sound. So those numbers are important because what we're going to do is we're going to draw the arrows to those sizes. So the first thing, we've got 20 joules going in, so I'm going to use 20 squares. And show that as my width of my first arrow. Now the next thing I need to do is to have 15 joules come in as heat. So I'm going to try and draw an arrow that has got a width of 15 15 squares. So I've marked on, there we go, 15 squares. Okay, from one side to the other, and the width of the arrow is now 15 squares. So that leaves me these 5 squares here to play around with. What I'm going to do is I'm going to form a little arrow coming off, and I'm going to let that arrow be about 5 squares in width. There we go, so that's 5 squares wide. So that's roughly now a Sankey diagram showing me 15 squares going forward, 5 squares coming off at a 90-degree angle. So I've now got my Sankey diagram drawn correctly. Now I can start to label this, because obviously I wanted to tell people exactly where each energy type is. So we've got electrical coming in on the left hand side. We've got our heat energy, which is passing straight on, and that's 15 joules. And then we've got our 5 joules of sound energy. Pause the video and try task 5. Let's have a look at the answer to task 5. We've got 25 joules of electrical energy entering the light bulb. So on the left hand side we need to have an arrow that is 25 squares wide. We have 10 joules becoming light, so that arrow needs to be only 10 squares wide. And then we have 15 joules becoming thermal energy, so the thermal energy arrow needs to make up 15 squares in width.